just linearly or near linearly, and that means that our regret will be a factor of log 1 plus t if we can show that most of the time, I mean, with exponentially small probability, our exploitation will be correct. Whenever we end the exploration, the negotiation phase, we got into the right position. But remember, they don't know how to do that. They need to negotiate in the blind. The surprising idea here is that this can be done by defining something called Markov chain. So every agent has a state, and he has some probabilities that are defined for the next states. And we can show that if they follow these probabilities with very, very high probability, exponentially close to 1, they will end up most of the time, their state is like what is the utility they got and whether they are happy or not, content or discontent. And we can show that most of the time the state at which they will be most happy under the algorithm that we proposed here will be the correct one. So with very high probability, we end up with the right allocation, and then they play the exploitation, and then this is repeated with longer and longer phases, and this way we can control. So this is for the simple case of multi-agent, multi-arm bandit. So basically, it's like a collision game. Whenever two gets into the same resource, they don't get anything because they collide. So the next step would be what we call congestion game. So what is a congestion game? Whenever more and more people try to use the same resource, the utility they get is lower and lower. It turns out that we can get similar results for congestion games. Strategies are more complicated because it's not sufficient to sample. We need to somehow coordinate the sampling phase, the exploration phase, with the other agents. But that can be done. This is in Review in Automatica, one of the control theory journals. So I will skip these things. So the bottom line is that even without communication, we can get near logarithmic. It turns out that if we allow some politeness into the protocol, that means whenever I want a resource, I listen and I ask, I see whether somebody already wanted this resource, I can get exactly logarithmic using something called the distributed auction algorithm that one of my PhD students developed in 2014. We can actually apply it into this learning context and get logarithmic regret just by the correct coordination protocol. So this coordination protocol is very much like what is done in Wi-Fi. You listen to the channel. If the channel is free, you take the channel, but you listen randomly. In our algorithm, you don't listen for a random period, but the time that you wait depends on how much you are willing to pay for that resource, and that allows you to converge in the right way. So these are the results, and then the general case is what is called Markov game. So what is a Markov game? A Markov game is basically a generalization of what is known as reinforcement learning. I'm talking now to the machine learning. So probably I lost like half or 2/3 of the audience, and that's fine at this stage. So a Markov game is a generalization of reinforcement learning. Reinforcement learning solves a Markov decision process. So you have a decision process that evolves in a Markov way, and then in a game, basically, both your action and the other's action affect your evolution. So that's much more complicated than an MDP, a Markov game. And then the solution, if we try just the usual, multi-agent reinforcement learning, that converges to Nash equilibrium. We already explained that Nash equilibrium is bad, so it is really challenging to solve Markov games without communication. That's part of the things that we are working on nowadays. Thank you.
Thank you, Amir. We have time for one question, if anyone has. If not, we'll ask Ilanit to set up. As you can see, we have interesting combinations of collaborators in terms of the project. We had more who collaborated with Yoav from the computer science. We had Amir and dsi from computer science and engineering, and now we have Ilanit from psychology and Ronnie Bauch from physics. So we're all excited to hear what it is.
Thank you. I'm going to represent Ronnie today because he's not feeling so well. So it's going to be more social sciences heavy than physics heavy. I apologize. But this is a true collaboration between us, not mine. Where is it? Okay, so we're interested in a question that's very big in organizational psychology, social psychology. What makes groups tick? We all work in groups, we study with groups, but what makes one group find the best solution, be creative and succeed, while other groups fail and deteriorate? And this is our team. So this is Ronnie, Yao Peng and Shachar sitting here. Hi. Yarden is not here today. But we have really a truly interdisciplinary team from physics, from computer science, from brain research. I'm from psychology. And with the support of this grant, we were aiming to try and use the data collected in my lab to answer the big question that I posited in the first slide. And our world is comprised of groups. We work together, we cooperate, we bring about action, social change in groups. And there's a big however, we don't really know the physiological dynamics at the basis of team development. So most of the work in organizational and social psychology is based on surveys, questionnaires, and observation. But we know from neuroscience and social neuroscience, which I do, that there's another level of representation which happens in the body, hormones, brain, physiological activity, which also explains many of the processes that we go through socially. So it's important to understand the physiological functioning underlying group behavior because it's critical to uncover the full picture of the ongoing exchanges that occur between group members. And we were wondering if physiological dynamics that emerge between group members during social interaction can help us predict team cohesion and team performance better than strictly relying on questionnaires and behavioral observations. So this is what we do in my lab on the third floor. This is, I'm allowed to show the faces because this is the research team. But people basically come in to do a group task together. Sometimes it's a verbal task like decision making. Sometimes it's what you see here, drumming together, which is nonverbal and helps us get better physiological signals. And they need to do something together as a group. And we continually monitor some aspect of their physiology, whether it's brain waves, whether it's autonomic nervous system activity. And we've already collected quite a big database that includes multiple physiological, behavioral, and psychological assessments during these kind of well-defined social group tasks. And the results I'm going to show today are based on data that we recorded from 498 participants in such tasks in 2 lab studies that involved face-to-face group interactions, drumming like you saw, and another which is more verbal, a decision-making task. And we first aim to predict psychological functioning from an individual level perspective, physiological functioning of the autonomic nervous system. And I'm going to show you results that are soon to be sent for review by Yarden and Yao Peng. And basically what they did here was they took a very interesting multidimensional approach to our autonomic nervous system. I don't know how much you know about the autonomic nervous system. It's a very complex and interesting part of the peripheral nervous system. And it's based on 2 branches, the sympathetic nerve and the parasympathetic nerve. And they continuously co-activate together when we're regulating ourselves in social environments. And the heart rate, for instance, is regulated both by the parasympathetic and the sympathetic branch in a very complex manner. Sometimes when we are highly threatened, the sympathetic nerve takes control. Sometimes when it's a more social engagement situation, it's the parasympathetic that takes stage. And sometimes they're kind of co-activating. And what we were able to show here is during baseline, before the group interaction even begins. So in the very first stages of just coming together and sitting together as a group before the task began, we can use these measures of sympathetic and parasympathetic balance of the autonomic space to predict negative effect and positive effect in people after the group task. So this is what you're seeing here. I don't have enough time to really delve into the meanings, but this was an encouraging aspect of the work that showed us that we can actually predict from strictly looking at the physiology at the individual level what kind of mood people will end up having when they finish their group task. We then went to a different approach, which is more interpersonal, not just the individual level. Interpersonal synchrony. This is basically the coupling of physiological functions between two people. And we know this occurs between individuals all the time in all the physiological functions, in the brain, in the hormones, in the autonomic nervous system. Obviously, it happens in behaviors. If I end up being really exciting in my talk and you give me a standing ovation, this is like seminal work from physics, you know how the claps go, right? This is synchrony. They first are completely chaotic, and then they become very quickly all at once, together, a bit slower, right? And then it moves out of that. This happens, these shifts like 6-7 times during a big standing ovation. But this is an example of total strangers coupling together in their behavior. This also happens in the physiology. And we know this acts as social glue, binds us together so we can cooperate and perform better, survive. And I'll give an example from heart rate synchrony. Our hearts synchronize, beat as one. We know this occurs a lot in dyads, in couples, in romantic partners, mother and infant. But we know much less about this in groups. So I'll give you an example of two groups in action, and this is the combined work of Yaopeng, Shachar, and Chen, who also isn't here but is a research assistant in my lab. And what you see here are videos after a lot of processing, a lot of thinking.